CSC 151 research presentation. We affirm that we have carried out our academic endeavors with full academic honesty by James, Adam, Leah, and Kyle.
A tree is a unique type of mathematical graph, where graphs are a structure made of nodes and the edges that connect them. A tree is defined as a graph with branches from one root node, depicted as the top node, downward, where each node must have only one unique path. The leaves of the tree represent nodes which do not split further.
This slide shows the file system on a computer. Notice that the two bins exist on the same tree, but this does not violate the tree because they are on different paths. / bin is not the same as / user / bin. Note that node is a spot on the tree where the path split, and root is the tree's first node. This slideshow is a flowchart, which is not a tree. Note that yes, you have your license, but no, you do not have a car ends on the same leaf as no, you do not have your license. A leaf is the bottommost position on a path. This is a tree. See how there are 3 different leaves of do not drive. If you have your license but no car, you do not end up on the same leaf as someone who does not have their license at all.
What is a decision tree? A decision tree is a tree where nodes check data conditions to determine the next node. Like in the tree to the right, the first node is color equals red, so it checks if the color is red and then determines the next node based on the condition. And most decision trees are generated and trained, and they're not designed node to node. An example of a decision tree is the automatic bot that's on different shopping websites. When customers need help from customer service when they're on these websites, the chat is sometimes started with an automatic bot to make sure that they are connected to the right department. And each input from the user determines its path to the final leaf to make sure they're connected to the right department or the right representative. In this example, the first node is the main menu, and then it breaks off between buying and refunding, and then the product, either it's furniture or a mattress, and then online or in store. Tree diagrams for chatbots can also get very complicated if there are a lot of different departments on the website. Different features that the company orders, such as order pickup, repair, or even speak to a live agent, can also affect the complexity of the tree diagram. Depending on what the customer inputs, it will determine their path to the final leaf and determine if the chat is automatic or if it will be connected to a live agent.
Most trees are designed via recursive splitting algorithms, which identify factors which splits the dataset in roughly even way entering a node. This process is repeated until the tree can identify the desired numbers of objects or types. As the initial tree is being created, a cost function is used to determine its accuracy. Pruning is then used, where branches or leaves are removed to create different leaves. If a removal does not improve the cost function, it is not kept. To the right is an example of a tree pruning decision tree. In the unpruned decision tree, the criminal record node was removed because it improved the cost function. There are a few important considerations for decision trees. Firstly is the cost function. A cost function is used to evaluate tree accuracy by finding the sum of the squares of the difference between expected and actual values. By minimizing this, we can improve the accuracy of our tree overall. Overfitting. When a tree has more nodes than is required to achieve the desired function of the tree, some nodes are considered non-essential and should be marked for removal to improve the accuracy. Underfitting. When a tree does not have enough nodes to decipher between the data types it receives. And data alignment. Trees should be aligned well with the dataset they are used on. For example, a tree's training data should be similar to what it will encounter when used in practice.
As discussed earlier, overfitting is a flaw in a decision tree where there are more nodes than is required for the given task, and thus the algorithm makes decisions on the basis of error and noise in the data. Consider, for instance, an algorithm for vocal recognition using a standard USB microphone. This microphone would have a range at which it could pick up accurate values and a range where it would pick up noise and natural fluctuations in the environment. If our decision tree began to make decisions on the basis of data from our error range, then the tree would be overfitted to the data set because it's beginning to read into error in the data and not actual significant trends which we are looking for. Underfitting, the opposite of overfitting, refers to when a decision tree does not have enough nodes to decipher between the data types it receives. Consider an algorithm which is supposed to take a picture of a number, 0 through 9, and identify it. Now imagine this algorithm is forced to be mapped to the tree on the left. As it must identify numbers between 0 and 9, this algorithm should be able to identify 10 discrete quantities. In fact, it must be able to identify 10 discrete quantities. However, the tree given to the left only has 7 leaves. This indicates that given its current node setup and configuration, our tree can make at maximum 7 choices. Recall, however, that it must be able to identify 10 distinct quantities, and since it can only identify 7, our tree is underfitted to the data as it does not have enough nodes to complete its task well. It is also important to discuss data alignment when discussing decision trees. Decision trees should be well aligned to their data, which means that at each node, a roughly equal amount of data gets sent to each subsequent node. Consider data flowing into point B. If this data was well aligned to the graph, we should see a roughly 50-50 split of data going to node E and node F. This does a couple of things. It helps ensure that our data gets evaluated in as few calculations as possible, which makes our algorithm more efficient. And it's also a holdover from the recursive binary splitting, which is used to create a lot of these decision trees. If a dataset is not well fitted to a tree, the results of the tree can be inconsistent and unpredictable. Take, for instance, facial recognition software, which has been developed by many large companies. The majority of these companies used test suites to train their facial recognition algorithms that were mostly white. And as a result, the final facial recognition algorithms proved to be far more effective on white individuals than African American individuals or Latino individuals because they had simply fewer members of those groups in the data that trained the tree. Acknowledging this discrepancy, both Microsoft and IBM have announced that they will begin retraining some of their facial recognition algorithms to take in cohorts of data which include more minority communities to make their softwares more accurate across all demographics.